Welcome back to class. This is Mr. Brain and we are on to quick class tutorial. Now, some of you already understand, many of the concepts we have discussed. I want to add to what we are discussing already to prepare you for your exam. Alright? So, I want us to look at waves. Okay? Okay? What is wave? Alright? Wave is a vibration that transfers energy from one point to the other. So there is a vibration or oscillation which transfers energy from one point to the other. Alright? But the medium itself is not displaced permanently. Alright? So there is an oscillation, but the medium oscillating is not displaced permanently. Okay? So we have types of waves. There are waves that require a material medium for propagation. Alright, those waves are called mechanical waves, okay? Mechanical waves. Then there are other waves that do not require any material medium for the propagation. They just vibrate through vacuum. Those waves are called electromagnetic waves, okay? Magnetic waves. So these are the two major kinds of waves. Waves can also be classified, alright, in terms of their nature of vibration and propagation. So now, in terms of nature of propagation or vibration, we have transverse wave, transverse wave, and longitudinal wave. Longitudinal wave. So what is a transverse wave? A transverse wave is more like what I have here. It's a vibration of material medium up and down. Okay, and it's an up and down vibration. Alright? But the wave motion is moving this direction. So that there is a kind of, perpendicular relationship, alright, between the vibration of the medium and the movement of the wave. So we say that transverse wave is a wave in which what? The vibration of the medium is perpendicular to the wave motion. That is for transverse wave. Then longitudinal wave, we say that the vibration of the medium is in line with what the wave motion. So while the wave is vibrating in a particular direction, or the medium is vibrating in a particular direction, the wave motion is also in the same direction. So the typical example is sound wave. So in sound wave we have a refraction and compression. Rarefaction and what? Compression. Now, if you notice this my diagram, you can see that there is a point where there is more compression. So what's happening here is that the air column, sound travels through air. The air column compresses and releases, compress and release. So this is the point of, rarefaction, okay? And this is the point of compression, okay? So that's what basically happens with air column, compression. So there is a rarefaction and there is a compression of air column. Alright, so you can see the vibration is this way, alright, and the travel is also that way. So they are in parallel to each other. So wave vibrate this way and wave motion also that way. That is for what? Sound wave. So now let's look at all what we have discussed so far. What are examples of mechanical waves? Examples of mechanical waves, sound. Why? Because sound requires a material medium. There is need for material medium. Water waves require a material medium. Every wave that requires material medium, they are all under what? Mechanical waves. Then the ones that do not require a material medium, you have your electromagnetic spectrum. Alright? The electromagnetic spectrum goes like this. V, Z. Alright? So this is for radio wave. Alright? R is for radio wave, infrared, Visible light, that is your light. Ultraviolet, then you have your X-ray, okay? Then gamma ray. This is what we call electromagnetic spectrum. Electromagnetic spectrum, okay? So these rays vibrate without and transfer energy from one point to the other without the need of what? A material medium. I hope you understand that. Alright, now down to this. Transverse wave. Examples of transverse wave. All these electromagnetic waves, they are all part of transverse wave. Why? Because their vibration is perpendicular to the transfer of energy or movement of waves. Are you getting it now? Longitudinal wave. A typical example is sound. Sound, you can see. I use sound as one of the examples of longitudinal wave. I hope you can understand this now. Alright? Alright, speed of wave. There are important terms that we need to know when we discuss wave. Alright, these are some of the things we know. Okay? So when we are discussing wave, first of all, we need to understand that if we represent a wave in a sinusoidal graph like this, okay? If a wave function is a form of this sinusoidal function, okay? You can see the vibration, right? Alright? So the maximum displacement, alright? The maximum displacement of the medium itself is called amplitude. So this is it. From here to here, amplitude. So what is amplitude? Amplitude is what? Maximum displacement of the wave particle or medium. Are you getting it now? So then we have another point here called press. Okay, that highest point is called press. Then this lowest point is called yaw. Okay, this is a yaw. Alright, so what is press? Press is the maximum point in a wave form. Okay, what is yaw? You can see yaw. Yaw is this lowest point here. Okay, so we have node and antinode. Node and antinode. So what would be your node? You can see your node is just all the points along, this direction. Okay, these are your nodes, right? What is antinode? You can see your antinode this way, right? That way. So now, what is the next one is the most important is your wavelength, okay? Wavelength. Now, what will be our wavelength? Our wavelength is simply the distance that makes a cycle. Alright, so what will make a cycle is from here, goes this way, come down here. That's a complete cycle, okay? So the distance from here to here is our wavelength. Alright, but for proper recognition, we rather say that the wavelength is what? The distance between two press, and this is press, two successive press, alright, two successive press or successive torque. That is what a wavelength represents, okay? That's for what? Wavelength. Then, when you now have your wavelength, of course, we can now get our what? Frequency. Frequency is the number of vibrations that will be made in 1 second, okay? So the number of oscillations that will be made in 1 second, that is what? Frequency. So frequency can be determined by what? Number of what? Number of oscillation over time. Number of oscillation, we can say oscillation over what? The time. Now, we now have period. What is period? Remember, frequency is represented by F and wavelength is represented by lambda. Okay, lambda. This is our wavelength. Then our period, period is represented by capital letter T. Period is different from this time here, okay? So period is capital letter T. Our period is what? The time it takes to make one oscillation. Just the time it takes to make one oscillation. The time it takes to make what? One oscillation, okay? So you can write your period as what? You notice that your period has inverse function. So your period is an inverse or reciprocal of your frequency. I hope you understand that. Your period is your, I think you get that period, okay? Period. Alright, so now, we want to understand the formula, okay, of wave function. The wave function, alright, have a sinusoidal, function. It's a sinusoidal function. So we say for wave, we have the what? A wave is, alright. Now for wave function, we have that what? Y is equal to amplitude, alright, sine, okay. If I have your Ks minus omega t, either way, it can be in this form, okay. Amplitude sine, alright, omega t minus your what? Ax. Alright, this is the function of wave. Now, I want to explain all the parameters you have here. Right, now this y is your what? Your vertical axis, okay, your A is your amplitude, alright, then K is called the wave number and your S is your vertical axis, and of course this is the time, and this is angular velocity, okay? So that is angular velocity. Now, for every function, angular velocity is equal to 2 pi over period, right? Angular velocity, that is, if you make, 2 pi represents one cycle. So if you make one cycle, over the time you use to make one cycle, that is your angular velocity. So if period is 1 over frequency, it means that our angular velocity is now what? When you slot this here, it means that angular velocity is 2 pi s. Can you see that? 2 pi s. Take note of that, alright? So now, remember that velocity can now be given as this, what do you call it? Lambda, which is wavelength, over period. Wavelength over period. Remember, wavelength is one cycle. Then the time to complete that one cycle, okay? So therefore, our velocity, this is a linear velocity, right? So now, when you apply the same principle here, wavelength over period means that velocity is f lambda. Can you see? Wavelength times what? Sorry, frequency times what? Wavelength. Can you see that? That is that about velocity. I hope you understand. Then the other things we have here, the wave number, alright, wave number K can be determined as K is that is 2 pi over lambda. Okay, our K is 2 pi over lambda, okay? 2 pi over lambda, that is our wave number, alright? So now, we want to be able to, when we factor all this into this equation, you will discover that everything will look, kind of look like this. Outside, alright, 2 pi f, right, ft minus what? When you put this one through, that's 2 pi, you have your lambda here, and your x, okay? You can factorize your lambda, so your equation could be in this form, alright, 2 pi, then every other thing goes this side. You understand what I'm saying? Every other thing goes this side, alright? So now, I hope you can see the board, alright, let's move back a bit. Okay, can you see the board now? Alright, so this is just a simple explanation of what is happening in our wave. So you have your xp minus x over lambda, alright? So now, we want to look at the properties of wave. What are the properties or characteristics of wave? Alright? Now, a wave can be reflected, very important, a wave can be reflected. So, reflected, or reflection, let's use the word reflection. So what is reflection? If the wave strikes a plane surface, it changes direction this way. Alright? That is reflection, alright? Light wave reflect, sound wave reflect, okay? The sound wave, the reflection of sound wave, you get the word echo, okay? Now, one of that is, we have wave can be what? Refracted. Okay, what is refraction? Refraction is mostly occurring in light wave. Okay, when light travels into another medium, this is air, alright, and it moves into another medium, it changes direction. Can you see? This is the linear direction, but it changes direction. That procedure is called refraction. So what is refraction? Refraction is the change in direction of wave when it travels from one medium to the other. Okay, So a wave can be polarized. Polarization. Now polarization is also for light. Remember, this is what happens in light. This is what happens in light. And it's all electromagnetic waves experience this. Alright, apart from sound. So a wave can be polarized. What does polarized mean? When a wave is made to pass through one plane. So this is vibration of the wave. Alright, these are all vibration of the wave. Okay? As they are advancing, they are made to pass through just one plane. This is just one opening. Alright? So what happens is that all the wave vibration that were light in this plane will pass through, every other thing will be absorbed. Every other thing will be absorbed. So at the end of the day, what you have here at this extreme end are waves of this format. Are you see? So when the wave is made to pass through a plane, that is the meaning of polarization, okay? So you have Polaroid, sunglass, these are all applications of polarization, okay? Now, a wave can be diffracted, okay? Now this diffraction is mostly happening in what? Sound. Diffraction. So what is diffraction? Diffraction is when, if you have an obstacle this way, and your wave is advancing, then once it passes through this obstacle, it spreads out like this. Alright, it begins to spread out. These are principles applied in sound wave. Okay, so this is diffraction. Diffraction is spreading out of wave as soon as it passes through a tiny opening. That is what? Diffraction. Okay, these are the characteristics. So we have superimposition, alright, and we have what do you call it? Wave can be superimposed, and there are other applications of waves that we're going to discuss, but I'll stop here for now. Thank you. Alright, welcome back. So we want to look at sound waves. Very important. Sound waves. Alright, sound waves. Sound waves. So what is sound wave? Now sound wave is the wave that requires a material medium to be propagated. Alright? Sound wave is a wave that requires a material medium, not just air, every material medium, alright, for it to be propagated, okay? So in sound wave, what happens in air is that the air is vibrating, okay? So there's a kind of compression of air molecules and rarefaction of air molecules. So you have a compression in this form, and you have a rarefaction, anything, and a compression, then a rarefaction, a compression, a rarefaction, yes? And this is what happens with sound molecules. So we call this a compression of air molecule, and this is rarefaction, okay? You understand? So this is compression, this is rarefaction. That's what happens with sound molecules.